Hello students, welcome to the course Network Theory. In the previous video, we completed the problems on Norton's theorem. So today in this video, we start the next theorem, that is maximum power transfer theorem. Okay, in short we call as MPT theorem also. Okay, so what is this theorem is about? Okay, so that we'll discuss today, and statement and proof. Okay. So to give an introduction, in circuit analysis, we are sometimes interested in determining the maximum power, okay, that a circuit can supply to the load. So far, whatever we have discussed in theorems, either we have voltage interested in the load current or a voltage across that load, right? Power part we have not considered, okay. So now to determine the maximum power in a circuit, how much it may deliver to the load, so that we're going to calculate. That is, we are interested. To do that, this theorem will help you. That's why the name maximum power transfer theorem. The transfer means, so from source to load it will transfer. That is the maximum power. Okay, so we will have a consider a circuit here A as shown in figure. Okay, so this is the circuit A, and you have the terminals AB and you have the load RL. Okay, so for this circuit, so this circuit A may be anything. It may be a DC network or AC network, any combination we have seen so far. Okay, so what we do is, we circuit A is replaced by its Thevenin equivalent circuit. Okay, so first part of the, in the problematic part, this will be helpful. Thevenin's equivalent circuit you will replace. So Thevenin's equivalent circuit means you will have the ETH in series with RTH. Okay, as seen from value AB, and we wish to find the value of the load RL such that the maximum power is delivered to it. Okay, so that is the thing. Okay, so when we will have, so when we have an Thevenin's equivalent voltage ETH and RTH, okay, so these two are in series and there is a voltage here. So when can it be possible? When it is having equal resistances. RL is equal to RTH, so you'll have the maximum power delivered to the or transferred to the load. Okay, so that theorem we'll try to prove. So there are three sub theorems are there here. Okay, any of this can be asked in exam. Okay, not all three. Okay, remember that. So we'll just try to elaborate the statement. So this is the statement of the maximum power transfer theorem. Okay, so just read out. In any linear bilateral network, maximum power is transferred from source to the load. When? So there are three instances are there. So in exam, whichever instance they call, that only you have to prove. Okay, so there are three proofs will come, and it is equal to three theorems. Okay, so in exam they can ask any of this combination. Okay, so keep in mind. Okay, so first case, when the load resistance is equal to the source resistance. Okay, so maximum power is transferred from source to the load when the load resistance is equal to the source resistance or Thevenin's resistance. Okay, when both things are resistance, this theorem holds good. Okay, that means you have the source also resistance and load also resistance. They should be equated. Okay, that is the maximum power. Second instance, you see, when the load resistance is equal to the magnitude of the source impedance. So at the circuit A side, you have the impedance, that means J term and all you have. So in that case, it is called as impedance. So in that case, it is not straight away equal to RL. Okay, which should be equal to magnitude. Okay, so that part we'll see. And the third case is both the source as well as load is impedance. Okay, so in that case, the load impedance is complex conjugate of the source impedance. Okay, so this is the theorem. Just once again read out. In any linear bilateral network, maximum power is transferred from source to the load when the load resistance is equal to the source resistance, or second, the load resistance is equal to the magnitude of the source impedance, and the load impedance is the complex conjugate of the source impedance. Okay, so these are the three subclasses in this theorem. It based on the completely based on the Thevenin's equivalent circuit. Okay, so whichever you can use it. So first we will prove this in this video, all these three sub theorems. Next video we'll try to solve the problem on each of these cases. Okay, so we'll go through the first proof now. Okay, the first instance we will consider. So where when the load and source resistances are purely resistive. So both the source and load have resistive. Okay, so this is an equivalent circuit here. So any circuit A is given, it should be converted into a Thevenin's equivalent circuit. For the proof sake, I have taken it as source voltage and source resistance. Es and Rs I have considered, and this is load. Okay, so very first I shown you know on circuit A. Okay, and then terminals RL is connected. Okay, so every time we'll consider the RL as load here. So from the circuit, so what is the load current? Okay, so we need to find power means what? So we have to find the IL into VL, or IL square into RL, or VL square by RL. That's why IL is the basic equation we require here, and we need to find maximum power. Okay, that instance also we need to find. Okay, from the circuit in figure, so Rs and RL are in series, so Rs plus RL, so voltage by resistance is current, so Es by Rs plus RL, make it as equation number 1. Simple. The power transferred from source to the load is given by, this is the equation for power, current square into RL, IL square into RL. So take the square of this equation 1, Es square divided by Rs plus RL whole square into RL. Okay, this make it as equation number 2. Okay, we'll continue the derivation, so you just note down and finally you can go through once again. Okay, so now we have to find the maximum power transferred to the, okay, so that will happen when the derivative of that power with respect to load is equal to 0. So that's why this is the standard one. The power transferred is maximum when derivative of power with respect to RL is equal to 0. That means what? From the power equation we need to take the derivative now. Okay, so derivations you are familiar already. Okay, so what is this? So this is a u by v form. Okay, differentiation of u by v form. So you need to have the formula here. What is the formula for differentiation of u by v? It is v into du by dx or du by dt minus u into dv by dt whole divided by v square. Okay, so you are more familiar with mathematics, so this is the formula of derivation I will use here because it is in u by v form. Okay, so here es square into rl acts as the u, okay, and rs plus rl whole square acts as the v part. Okay, so if you apply this formula, what will happen? V rs plus rl whole square into es square is constant, rl, so differentiation of rl with respect to rl will give you 1, minus u is e square into rl dv by dt. So what you have here, rl, right? So 2 into rs plus rl into inside function, rs is 0, rl becomes 1. Okay, so 2 rs plus rl you'll get, divided by this is square square. Okay, rs plus rl square whole square will come. Okay, so just see that equation, note down this formula required here in all the three cases. Okay, so that is the formula I have applied. So rs plus rl square into e square into 1 it is. Okay, not written. E square into rl 2 into rs plus rl divided by rs plus rl 4. Okay, so now in this above equation e square is common, and here rs plus rl 4 is square. If you take this both right side, rs plus rl to the power 4 divided by e square will come. Okay, that multiplied by 0 is 0. That's why straight away I have written 0 here. Okay, I have not shown that part, hope you understand. Okay, so then what is remaining? Rs plus rl square minus, so this e square is cancelled out, so 2 rl rs plus rl equal to 0. Now simplify, this is a plus b whole square, so this is also the standard formula, a square plus b square plus 2ab. Okay, so rs square plus rl square plus 2 rs rl minus, multiply this 2 rs into rl minus plus minus minus 2 rl whole square equal to 0. So this will cancel out here, plus minus, and here rs square is there, rl square is there, minus 2 rl square is there, so it will give you minus rl square, which is equal to 0. So if you take this rl square right side, and if you rearrange the equation, what you will get, rl square is equal to rs square. So if you remove the square, so you'll get rl is equal to rs. So this is the proof of the first theorem. Simple. So you write the current equation, load current, then take the power equation il square into rl, then differentiate that and equate to 0, and solve that, so you'll get the rl equal to rs. So this is the same strategy, we'll use it for all the three cases. Okay, so this is proved here. source resistance equal to load resistance, then power is maximum. Okay, hence maximum power is transferred from source to the load when RL is equal to RS. So that is the proof. Under this condition, what is the IL? ES by RS plus RL. So RS also I will substitute RL, so it will become ES by 2RL, and the maximum power transferred is given by IL square into RL. So now we'll substitute this IL. So ES square by 4 RL square into RL. So 1 RL cancel out here. So what is remaining? ES square by 4 RL. Okay. So this is the, you can resistive network if you want to find max. So they will tell you to find the load resistance and also the maximum power. Okay. So load resistance will be calculated by finding the some circuit will be given, RTH you are finding, right? So that RTH you have to equate it to RL. Okay. So then to find the maximum power, you have to use this equation, ES square by 4 RL. You have to substitute and you will get the maximum power. Okay. So that is how the problem will come. Now we'll take the second case. Okay, where the source is having impedance and load is a resistance. Okay. So hope you are noting down. Pause the video and note down. When load is purely resistive and the source has impedance. Okay, so this case we are considering, so ES, you can consider AC also, no issues. And this is a source impedance now, ZS, okay, which is nothing but RS plus JXS. Okay, and this is a load resistance. Okay. This type of circuit you have with the, so ZS is we have considered as internal impedance of the source E, okay, as shown in the circuit diagram. Again, same way, procedure is same. Write the equation for current now. I is equal to, okay, just I have considered, it is nothing but IL only. Okay, IL is equal to ES by, so source is only one, voltage is only one, ES divided by equivalent impedance. So RS, ZS is nothing but what? RS plus JXS plus RL. So this is how we have written Ohm's law. Okay, so this is from Ohm's law. Okay. So we'll continue the, so next part is finding the, writing the power equation. So this we will simplify before that. So we have the complex term here. So ES by RS plus RL. So the real term, real part we have grouped it and imaginary part separated it. Okay. So now we'll take the magnitude of this. Okay. So what is magnitude? So when you have A plus BI form. Okay. So its magnitude will be always square root of A square plus B square. Okay, J term, removing the J term. And angle is always tan inverse of B by A. So in the calculator you are converting from polar to this, you are doing, right? So manually doing is this formula. Okay. So if you want the magnitude, you will take square root of A square plus B square, and angle is tan inverse B by A. You can do like this also. This will take much time. Calculator is available. That's why we'll normally use calculator, right? Previously we have done in mesh analysis, node analysis. So finding the rectangular form, polar form, you have done it. Okay. So this is the manual term. Okay, how it is going to implement that. Okay. So that only we have used here. So real part square, which is RS plus RL whole square, imaginary part square plus XS square. Okay. Angle is not required here. Only magnitude part I have considered. Clear? Then we have to write the power equation. Power consumed by the load is given by I square into RL. Okay, I we have considered, it's square into RL. So which is, just substitute this equation into RL. ES square by, so here I square is there, square root will cancel out. So RS plus RL whole square plus X square will remain. Okay, into RL. Okay, so this is the power equation. So same way, the power transferred is maximum when derivative of power with respect to load resistance is equal to 0. Okay, so if you find out that, so what will happen again, U by V formula. So it is V is what? RL plus RL square plus X square, same as it is I am writing, into differentiation of V form is RL will give 1, ES square is constant, so it will remain. Okay, minus U is ES square into RL into differentiation of this term. Okay, 2 into RS plus RL, same thing will give. XS is not related to RL, right? So that's why it will be 0. Okay, it acts as a constant and it will be 0. So this is what the you will get, and here you have the square. So if you cross multiply this, you will get the 0, and even the ES also. ES if you take outside and if you write below that, and you cross multiply. So ES also will cancel out. So remaining part only will write this. So this RS plus RL whole square plus X square and RL into 2 RS plus RL. This only we will write it and equate it to 0 and we'll solve it. Okay. So just note down this. Okay. Simple derivations in the same manner. So that is what I told you, RS plus RL square plus X square. To we have equated, that is equated right side I have taken, or else you can write minus into equal to 0 also you can write. So from which we get RS plus RL square, a plus b whole square formula, RS square plus RL square plus 2 RS RL plus X square is there already. Here we have multiplied 2 RS RL plus RL square. If you take this right side, it will become minus. So that's why straight away cancelled here only. So now we will take 2RL square left side and equate to 0 again. So RS square, RL square, whatever is there written as it is, then minus 2RL square equal to 0. So RS square, after that X square I have written, and then RL square minus 2RL square will give you minus RL square. 1 minus 2 is minus 1, right? Equal to 0. So now RS square plus X square. So this minus term I have taken right side, it will be RL square. So now to find RL, what you have to do? So you could not write straight away RS plus XS here, right? It is in square form and plus is there. So it's why it is square root of RS plus XS square. So what is meant by this? There is nothing but the magnitude of ZS. Okay, so initially we have considered ZS is nothing but RS plus JXS. So what is its magnitude? As just before I told you, A plus BI form. It is real part square plus imaginary part square. So that is what you got here. That's why it is written like this, magnitude of ZS. Okay. So RL is straight away not equal to ZS now. It is equal to magnitude of source impedance. In the case of source, you have impedance. Okay. This is the second theorem. So we have proved it. RL is equal to ZS. Okay. Is it clear? Okay. So power, maximum power part will not change much. So thus the power transferred from the source to the load impedance is maximum when RL is equal to ZS under this condition. Okay, what is that condition? If you have the source as impedance. The maximum power transferred will be same. You can use this equation because RL is calculated here from this magnitude and IL is there with value. So just multiply. So you'll get power. Okay. So either you can use this, okay, or the previous one only you can use. So next last part, if you have source and load both are impedances, okay, that also prove. So majority of the time this is asked, okay, majority of the question paper. So this theorem is normally asked more times, okay, compared to the previous two. Okay, previous two normally they will ask problems, more problems on first two variety, but this they could not ask for. That's why they will give you in theorem proof. Okay, so that's why this is very important, I say. Okay, so how to do this? A little bit variation is there. Okay, when the both and the load source have impedances, the circuit will look as shown. Okay, so ES, ZS and ZL. Okay, and again current I is considered. So both are here in complex conjugate form. So ZS is considered as RS plus JXS, RS plus JXS, and ZL is equal to RL plus JXL. So like that we will consider, and we'll same way we'll do that. Write the equation for current, simplify that current, and then write the power equation, then take the derivative equal to 0. Okay, same way. So let ZS equal to RS plus JXS, that's what I shown you, be the internal impedance of the source, and source ES, and ZL is equal to RL plus JXL be the load impedance as shown in the circuit. This is the sentence you have to write first. Then from figure I is equal to ES by ZS plus ZL. So substitute for ZS and ZL, RS plus JXS, RL plus JL. So group the real parts here and imaginary parts. Okay, so what you'll get, ES by RS plus RL, and here JXS plus XL. So now take the magnitude here. So I is equal to ES by, so A square, that is the real part square, RL plus RL square, plus imaginary part square, XS plus XL square. Okay. So this is the magnitude part. Angle we have not written because we are interested in only magnitude of the current to find the load power. Okay, make it as equation 1. Then power delivered to the load is I square into RL. So this is the same equation. So just square root will cancel out and ES will become ES square divided by RS plus RL whole square plus XS square RL into 2. Okay, so here also this will not change. Okay, so load is RL only. Okay, although we have considered ZL here, but we are considering only the real part, right? So that's why power is considered not ZL, it is considered RL because it is in the part only, right? RL plus XL is there. In that, RL is the real part. Okay, so RL is the real part. So with respect to that, we are considering. Okay, so that's why I square into RL only. So now this is the equation 2. Okay, whereas in the denominator you have the load, this one. Okay, reactance. So now what we will do is we'll derive this with respect to, there are two cases are there. Okay, so first case we'll derive this power with respect to reactive load. Okay, dxl is equal to 0 we will find, and whatever equation we will get, okay, we'll make it as p1, and then that p1 will derive by drl. Okay, so that we'll get the both the part. Okay, xs part also and rs part also will get. So this both we are equating to 0 one by one. Okay, so that part we will see next. Okay, so in practically this is like a tuning circuit. Okay, so when you tune that, when you will see maximum, okay, graph, right? So like that it is, but here in mathematical way we'll do like this. Okay, our idea is to adjust the load parameters RL and XL so that power is maximum. Okay, so P means power and here it is maximum, maybe mixed it. Okay, so P is maximum. So for that we are adjusting the parameters RL and XL. To set this, to do this, what we'll do, we set dP by DRL and dP by DXL equal to 0. Okay, so one by one we are going to do that. So first case we'll consider the power transferred is maximum when with respect to load reactance. Dp by dxl is equal to 0 we will consider. So we'll take the ratio same way, u by v formula. Okay, so what will the change here is, sorry, so here you don't have any XL terms. Okay, in that means that completely it will acts as the constant. Okay, so v into du by dx will give you 0. That's why this left part is completely 0. Okay, and second part minus. Okay, so that is same formula, u es square into rl, and when you consider this part, again here this part does not act, so it will be 0, and in this part you have 2 xs plus xl. Okay, and xl becomes 1, dxl by xl will give 1. So 2 xs plus xl into this part with minus sign will come in the numerator. Okay, so left side it is 0, that's why it is not considered. Okay, so you are well in applying the formulas. Okay, mathematics. Okay, so here this part will come 0, which is that part v into du by dx. Okay, because u is a constant here, that's why differentiation of constant will give you 0. 0 into v is 0, that's why this part is 0, minus. Okay, you have u into dv by dx. So what is u? So this minus sign is already there. So es square into rl was there in the u. Okay, and this 2 into xl plus xs. Okay, so differentiation of the v will give you this answer, that is written like this. And this denominator v square, so you'll have v square in the denominator, so that is nothing but this whole square will come equal to 0. When you cross multiply this, so this term equal to this will come, so minus 2a square rl xl plus xs equal to 0. So this complete three terms, if you take the ratio 0 by this, so it will be 0. What is remaining is xl plus xs is equal to 0. So by setting this parameter we got xl is equal to minus xs. Oh, okay, make it as equation number 3. So it is not over, xl part we got, xl is minus of xs, source reactance. Okay, this we got. Now what we'll make, so we'll substitute xl equal to minus xs in the first power equation. Okay, so in this equation we will substitute XL equal to minus XS. What will happen? XS minus XS 0, so this part completely becomes 0, right? What is remaining? ES square into RL by RS plus RL square. So that we consider as P1, and that we derive it with respect to RL now. Okay, to get the RL part. So first time it may not be easy to understand, so you write down and again go through my video. Second time you may understand and write down. Okay, so this first part, so now this I have made. Okay, substituting XL equal to minus XS in the second equation, I got ES square RL by RS plus RL square. Now I will derive the power transferred is further maximum when dP1 by DRL is equal to 0. So it is like a box, it will come impedances. Okay, reactance box and resistance. So you'll be keep tuning, right, when the power will come maximum. Okay, here in theoretically when proving, we could not have knob and all. Okay, in practically we can do that. Okay, it will also come same. Even that theorem proof and all, it is there in earlier this one lab programs, but now you don't have, I guess. Okay, so that is the thing. So now we'll do this derivation same way. U by V formula, V into du by dx. Okay, so here RS plus RL square is the V into ES square. RL will give 1. Okay, minus ES square RL 2 RS plus RL divided by it's 4 equal to 0. This is similar to first equation. Okay, first proof we have done now same way. So again ES square is common here both. So this if you take outside and take the ratio here, so this term will vanish out. So remaining is RS plus RL whole square minus 2RL RS plus RL. Okay, so you'll equate it, simplify, and what you will get, you know already. So RL is equal to RS. Straight away I have written because you know already in the first part we have done. It is RS square plus RL square plus 2 RS RL minus 2 RS RL minus 2 RL square. So this plus minus cancel out. RL square minus 2 RL square will give you minus RL square. So RS square is equal to RL square will come. So if you remove the square, so you'll get RL is equal to RS. Straight away I have written. Okay, so hope you are understanding this. So you write it. Okay, the steps. Now combine the equations 3 and 4. 3 what you got? XL is equal to minus XS. So it is written here. And RL is equal to RS from 4. Combining equations 3 and 4, we can conclude that for maximum average power transfer, ZL must be selected such that XL is equal to minus XS and RL is equal to RS. That means we will write now ZL. ZL is nothing but what? RL plus JXL, and which is equal to now RS. RL is equal to RS we have made, and JXS we have made. Okay. What is this minus term? So what is ZS? It is RS plus JXS. This is ZS. But there is a minus sign, means what? It is a complex conjugate. That's why complex conjugate is shown with this symbol. Okay. So ZL is equal to ZS complex conjugate. Okay. So that is how we have proved the third theorem also. So that is the maximum average power of a circuit with an impedance ZS is obtained when ZL is set equal to complex conjugate of ZS. Okay, so that is a proof. So setting this value RL equal to RS and XL equal to minus XS in equation 2, so we get the maximum power transferred is same equation. PL is equal to ES square by 4 RL. Okay, so with this we have completed the proof of all the 3 theorems. Just we'll summarize once again the statement I will tell. So we have done all the proof now. Okay. In any linear bilateral network, maximum power is transferred from source to the load when the load resistance is equal to the source resistance. RL is equal to RS when you have both resistance. And if you have load source is impedance, then load resistance is equal to the magnitude of the source impedance. And third case, the load impedance is equal to the complex conjugate of the source impedance. Okay. So to understand it still further better, you may be understood now 20% or 25%. To make it full, so we'll solve problem on each of this variety in the next video. So then it will be more clear to you. Okay. When they are giving problem, so they will give like this. Okay. So the circuit A, you have to reduce it into a Thevenin's equivalent circuit, ETH into RTH. Then that RTH you have to make it equivalent to RL. and then you have to use the power equation, IL square into RL, you'll get the power. Okay, it's very simple theorem. Okay, so only thing here is proof. All the three proof you have to learn. Okay, anyone they can ask. Okay, as I told you, third party is asked more because problem asking is difficult. That's why they will ask maybe. Okay, but you could not stick. They can ask the first one also, second one also asked, but more frequently asked is that. Okay. Okay, thank you. Hope you have got something. Okay, so go through once again, write down everything. Okay, and in the next video we'll solve the problem on this. With that we will complete the module 2, network theorems. Okay.